This is our big theorem we saw last time. I just rewrote it. I mean, we saw it on the board already, but one of our big tests is going to be prove this theorem. Okay. By the way, I'm still diligently working on your exams. They'll be done soon, I promise. Maybe another day or so. Okay, they're getting there. So anyway, we stated this theorem. So we were talking about primitive Pythagorean triples last time and asking some questions like, are there infinitely many? And if so, can we describe them all or generate them all? And I mean, we did already settle the fact that there are infinitely many, but this theorem tells us exactly what they all look like. Okay, so there's a recipe for them. So I mean, there's two sides to this theorem. The one is sort of the classification that says if you have a primitive Pythagorean triple, it has to fit into this structure. So it tells you a lot of things. C is going to be odd. One of A or B is even, the other one's odd. And here's where they come from. So there's going to be a pair of integers that determine A, B, and C. So there is a pair of relatively prime integers, M and N. So they're relatively prime, and they have opposite parity. So one is even, one is odd. Such that A, B, and C are completely determined by M and N in this way. Okay, and then the other side of the story is that if you look at it the other way and you start out with an M and an N and try to build an ABC, it will always give you a primitive Pythagorean triple. So you can think of it, that last remark is like, well, this is a generator for making primitive Pythagorean triples. Just pick an M and an N that satisfy the requirements and then build them. And then the rest of the theorem, which is the harder part, says that that's the whole family. Like, you didn't miss any. Like, so this recipe for building a primitive Pythagorean triple will build all possible primitive Pythagorean triples. Okay, unlike some of the recipes we were looking at last time, which made primitive Pythagorean triples, but they didn't get them all. Okay, so this is the more complicated full picture. So that's our big task for today, though, is to see if we can prove this theorem. And we looked at some examples last time of generating them, where you just pick an M and an N subject to these requirements. So anyway, just to begin, there's kind of a lot to do this, but we'll sort of start with the last remark here, which is that if you build something this way, it will be a primitive Pythagorean triple. So let's start with proving the last assertion. Okay, so anyway, suppose what that means is suppose we have an A, B, and C given by these formulas. So suppose we have A is n squared minus m squared, B is 2mn, and C is n squared plus m squared, with m and n as described above in the theorem statement. So what that means is, one is even, the other one's odd, and they are relatively prime. Okay, and so the first goal then is to show that this thing is a primitive Pythagorean triple. Okay, so you can start by just checking that it's in fact a Pythagorean triple. So then what happens? Let's say this, so ABC is going to be a Pythagorean triple. Okay, because we could just do some algebra to check, let's do it up here. So if you look at A squared plus B squared, we have formulas for A and B. So A is n squared minus m squared, and B is 2mn. And we can do some algebra to these expressions. So what this is A squared. So A squared plus B squared would be that. So if you square out the expression for A, you'll get n to the fourth minus 2n squared m squared plus m to the fourth. And if you square that other thing, you have 4m squared n squared. Okay, and then there's like terms you can combine here. Right, so this is This looks like n to the fourth plus 2n squared m squared plus m to the fourth. Right? And that's from combining these things. And then that's a perfect square. That's actually n to the fourth, sorry, n squared plus m squared quantity squared. That's the same thing. So you can factor that up as a perfect square. You can say, well, yeah, that's c squared. Right? That's then getting squared is what was c was defined to be. Okay, so that shows it's a Pythagorean triple. Okay, we still have to show it's a primitive Pythagorean triple. Okay, so there's something about this. If we just pause for a second, which is this recipe. If you take an m and an n, and if you don't pay any mind to what sort of integers m and n you take, this will always generate a Pythagorean triple. Okay, what is kind of the point is these extra assumptions on m and n are what's going to make it primitive. Okay, so something you can check if you want is if you just grab an m and an n that don't satisfy these extra requirements and you make this thing, you'll see it'll come out to be not primitive. So it's something you can try with some examples just to see. But we're going to show it's primitive with these extra assumptions. So we want to know why it's a primitive. Primitive means there's no common divisor amongst all three of A, B, and C. Okay, so we need to show that the common GCD of A, B, and C is 1. So one way we're going to deal with arguments like this today is maybe slightly different than what we did before. But to show things have a GCD of 1, one common tactic is just to start out by assuming they have a prime divisor and prime common divisor, and then just get a contradiction somehow. Okay, so we'll do something like that here. So we'll suppose P is a prime, which divides all three. So P divides A, P divides B, P divides C. Okay, and then we'll hit a contradiction somewhere, and that'll mean no such thing can exist, which means they have no common divisors, no non-trivial common divisors. So anyway, the point is just, first of all, right, so what we do know, by the way, is that C is odd. So what we're really, I guess like this, strictly speaking, isn't in effect here. What we're doing is we're taking an m and an n, one even, one odd, and building this relatively prime as well. So I guess the point is just that since we know one of n and m is even, the other one's odd, just a quick observation is that C does have to be odd, right? Because square of an even is even, and the square of an odd is odd. So first of all, just note that C is odd. This is because one of m and is even, the other's odd. Okay, and so then the point I just want to make is that in this scenario, P is not 2. Oh, sorry, I forgot to finish my sentence. So this thing is odd because of that fact. So the point I just want to make is P is not 2 in our scenario. But I said suppose we have a common prime divisor. It's not going to be 2 because C is going to be odd in this scenario. So then anyway, the way these kind of arguments go usually is playing around with linear combinations. Okay, so what is true is so if I know P divides A, B, and C, I can get that P is going to divide linear combinations of A, B, and C. And in particular, a good linear combination to examine is something like A plus C. Like look at A plus C. If you add A to C, the m squareds cancel. So what happens here is P divides A plus C. And since they're defined this way, right, that looks like n squared minus m squared plus n squared plus m squared. So this is 2n squared. Okay, so if you have a prime divisor of 2n squared, means you know the prime is not 2. That's going to imply it has to divide n squared. Okay, so this implies p divides n squared because it's not 2. And therefore, because it's prime, it divides n. Right, if a prime that divides a product like n times n has to divide one of the factors. In this case, they're both n. So anyway, p divides n, and you can make a similar argument to see why p divides m. So a similar argument would be, rather than consider the sum, you can consider the difference. I guess the difference maybe to consider is c minus a. Right, so c minus a is n squared plus m squared minus n squared minus m squared. So the way this one's set up, the n's cancel and this is 2m squared. And so a similar argument tells you, again, since p is known to not be 2, it would have to divide the m squared, and that implies it divides m. Okay, so where we're at is that this is going to contradict the fact that m and n are relatively prime. But your question.
How do you know that the p doesn't divide the 2?
Well, because I just made this careful argument to say it's not 2.
Okay.
Right. So I mean, it's if it divided 2, the only prime that divides 2 is 2. Right. Right. So we already ruled out that it can't be 2. That's why that little thing was spelled out. Did you have a question? Or?
Yeah. Could you also say p divides, since p divides b, that p also divides m, since it's not 2. You said
Oh.
that.
Well, because right. So, well, you would know it divides one of n and 4n.
Right, and we already said it divides n, right? Or yeah.
No, well, no. We're trying to say that it divides both n and m.
Right, but since we already said that it does divide n, then
Yeah.
we could just say that it also divides n, right?
Well, no, because you would have to start with b, right? Like when
Yeah.
You could start here and say, oh, well, it divides m or n because it divides this product. So then, which one is it? I don't know. Like maybe it's m, maybe it's n. You could start out by saying, well, okay, let's suppose it's m, and then you make this argument to learn it divides n.
Yeah.
But it might work out the other way, where if it starts out here, well, it divides this, maybe it's because it divides n, then you'd have to go and make this argument to get that it divides m. But you couldn't do one of these and then go back to that, because like you might learn it divides n from this statement and then go back up here and say, well, I know it divides this triple product, so it divides either m or n. But it divides n, so it's that, and so you don't learn necessarily it divides n. So I mean, you could kind of like start with that, but you still are going to have to do one of these to fill in the gaps to get both. But it also works kind of nicely just to do them simultaneously. Yeah. So anyway, the point though, just what we've got. This is a contradiction. So this contradicts the fact that the GCD of m and n is 1. Okay, so what we've just done is made an argument that as for y, no such prime exists. Okay, so no such prime can exist, and therefore, so no such p exists. So that means the GCD of A, B, and C is in fact 1. And so that completes the proof. It had to be primitive. So I mean, we really just accounted for this further statement, right? Like, so if we build one this way with all the assumptions on m and n, then in fact we get a primitive one, primitive Pythagorean triple. Okay, and so the actually harder part is the rest, like to show that if you had an arbitrary primitive Pythagorean triple, it has this structure. So that's what we're going to work on doing now, but it will take a little bit more effort than this, so we'll have a couple lemmas just that we'll need to lean on. So anyway, this has been part of the proof of this theorem, just this last part, and then we'll do a little intermission and set some things up before we do the rest of the proof. So if you have any questions, any more questions on this thing right here? Okay, anyway, I'll just leave it to you to check. But something you could try. I mean, it's pretty evident, by the way, if M and N are not relatively prime, if they have a common factor, then that common factor will divide all three of these expressions. So you'll definitely get something not primitive. What's a little more interesting to observe is just if, like for example, if you take them both to be odd, you'll get something that's not primitive as well. I guess maybe it's kind of evident that everything will be even if you look at it, but okay, anyway. You guys have any questions before we dive into some preparation? So we're going to have a couple of lemmas. So before we prove the rest, what we'll do is look at some lemmas. Two lemmas, really. So here's one. So here, the statement is going to be about perfect kth powers of integers. We'll be interested in talking about perfect squares for the context we're looking at, but we'll just state something a little more general here. So k is going to be an exponent, like squaring or cubing or something. And here, suppose a and b are relatively prime. So we're going to have relatively prime integers with the property that when you multiply them together and consider their product, it's a perfect kth power. So this is a kth power of an integer. Like a perfect square, for example. But the two factors were assumed relatively prime, and the conclusion is going to be that actually each of the two factors is also a kth power. Okay, so then each of A and B is also a kth power of an integer. And again, we'll be interested in applying this when k is 2, but it's not any harder to establish when for any k. So just to give a quick argument, this one relies on prime factorizations, and we'll just lean on this fact we mentioned in the past, that you can tell that a number is a kth power of an integer by looking at its prime exponents and its prime factorization. So an integer is a kth power if and only if all of its prime exponents are multiples of k. So that's the main fact here. And so you just look at prime factorizations. So you can write out the prime factorizations, say like this. So I'll write them on 2 lines. So you could take A, and I'm going to write it this way. Say P sub M to R sub M. And then we could look at one for B. That. And the understanding, since I'm writing these with exponents, is that these are prime factorizations like into distinct primes. So P1 and P2 are not the same prime, because if they were, I would lump them all together into one single thing with one exponent. Okay, so these are into distinct primes. That's what's meant by that. And so anyway, since you know that A and B were assumed relatively prime, right? So since A and B are relatively prime, what that means is there's no primes in common here, right? So none of the P's are equal to any of the Q's, right? So since these are relatively prime, the point is that P sub I is not equal to Q sub J for any ij. Because if they had something in common, they wouldn't be relatively prime. So then the point to quickly follow here is that when you actually multiply them, so when you multiply A with B, then when you look at it from the prime factorization perspective, here you have this. Okay, and the point is that since there's no common primes, like this is sort of like simplified, so to speak, as a prime factorization, right? So none of the p's are equal to any of the q's. If they were, you would want to then combine them further, but they're not. We just said that. So this is the prime factorization point is that this is the prime factorization of AB into distinct primes. This is the key point here. Okay, and once you're looking at the prime factorization of a number into distinct primes, like if you know it's a kth power, that means all the exponents are multiples of k. Okay, so since point is that since AB is a kth power, all exponents are multiples of k. So all the exponents across the board here. So that is to say, k divides, r sub I, and k divides s sub j for all ij. Okay, and that's exactly what you need then, because when you go back and say, like, look at A, well, now we just said that all the exponents up here are multiples of k, and that implies A is a kth power. Okay, so for example, then this implies that A equal, A, which looks like this. Sorry, P1 up to the R1 up to Pm to the Rm. This is a kth power of something because its exponents are all multiples of k, we just learned, and also p, right? Okay, but anyway, this little lemma like absolutely relies on them being relatively prime, otherwise it's not going to work this way. Okay. Hope that's okay. So that's not super deep, but it's something we'll use at some point. Okay. Okay. Another lemma, which is of a very different sort of flavor. There's going to be a lot of discussion of even and odd. You can kind of tell this from all this. The way the theorem is stated, talking about various things being even and odd and so on. So here's just a little brief lemma about squares of evens and odds. So this is sort of two facts, first of which is stated as two things. So the square of an even number number is always divisible by 4. So this is let's say is divisible by 4. Okay, that'll be really easy to see. The second assertion is a bit more interesting, which is about squares and odds. So the square of an odd number is actually always one more than a multiple of 8. So it's one more than a multiple of 8. Okay, so we'll see why in a second. So let's just quick proof. This is really fast. At least the first one's really fast. I mean, being even just means you're divisible by 2. So like if, say you have a number n that's even, it looks like this. So j is an integer there. Then, clearly when you square it, right, you square 2j, which means you get 4j squared. So it's like pretty obviously a multiple of 4, right? So that's a short proof. So this is a multiple of 4. Okay, that's the even one. suppose you start out with something that's odd. So an odd number would always look like this, right? It looks like one more than a multiple of 2. So what happens if you square it? So if you square it, of course that means 2k plus 1 gets squared. Then you can do your algebra to say this is 4k squared plus 4k plus 1. Right? And so what you can see at first glance here is a weaker conclusion. So we're trying to say something stronger than what's immediately evident right now. What's immediately evident right now is that it's one more than a multiple of 4. Right? So it's 4 times something plus 1. Now to say that it's 8 times something plus 1 is saying something stronger. And so maybe it's not totally clear at the moment where does that come from. So let me show you where it comes from. So you can do a little bit better here. And so when you factor this, you can factor this as k times k plus 1 and then plus 1. Okay, and so here's then the slightly clever observation is that these two factors, right, k and k plus 1, those are consecutive integers, right, one after the other. Right? If you have any two consecutive integers, one of them's even, right? One will have to be even, the other will have to be odd. Like which is which depends on k, but certainly either k or k plus 1 has to be even. And the point then is that there's an extra factor of 2 sitting in one of those numbers. So that'll bump you up to 8 times something here. Okay, so anyway, to finish this little argument, what happens is since k or k plus 1 must be even, what happens is that 2 is a divisor of the product k times k plus 1. Okay, and so what happens then is therefore, if you look at this thing that we had, which is 4 times k plus 1, this is going to have to be divisible by 8 because there's a factor of 2 somewhere in the product of k times k plus 1. Okay, so that's really then what we get then. So this is some multiple of 8 plus 1. We actually won't need this result, the stronger form of this that we just proved. We'll only actually need to know what's one more than a multiple of 4 for what we're about to use it for, but it's just, might as well prove this because it's a nice little idea. It just takes a little bit of extra effort to get a stronger statement. Okay, so that's the argument. So you can check it though. Anytime you take an odd number and square it, if you take 1 away from the result, it should be divisible by 8. Okay, so we've done all this groundwork. We proved a couple of lemmas. We're ready to get back to this thing, okay, for real. So we're going to start out then to prove this, the main part of this theorem. We're going to start out with an arbitrary, primitive Pythagorean triple, and then we're going to just get to work proving all these various assertions. Okay. So this is the end of the lemma. And we're ready to properly prove this theorem 5.5, at least the main part that we didn't prove yet. So we're going to start by saying, let's let A, B, C be an arbitrary, primitive, Pythagorean triple right, so what that means then, is we know a squared plus b squared is c squared. And on top of that, we know that the GCD of a, b, and c is 1. That's all we have to work with right now. Okay. And so we have a lot to prove. In particular, we have to prove all these parity assertions, about c is odd, and one of a, b is even, the other is odd, and all these things. And then we're going to have to figure out where the n and the m come from. Okay, so let's start out by thinking about A and B and what would happen if A and B were, say, like both even or both odd. Okay, so easy case to consider, if A and B are both even, then certainly what's going to happen is that C well, C squared will be A squared plus B squared. What's going to happen here is that the right-hand side is now known to be even, right? So this is even. In fact, I mean, we could even say divisible by 4. Because we just said squares of evens are divisible by 4. So right-hand side is divisible by 4, and therefore C is divisible by, well, C squared is divisible by 4. So this implies that C is even too. Okay, this can't happen. If A, B, and C are all even, then they're not primitive, right? That would mean they all have a common divisor of 2. So this can't happen. This implies GCD of A, B, C is at least 2, right? So that's a contradiction. Okay, so that can't happen. Now, we're also saying that they can't both be odd, so we have to figure out why that can't happen. Okay, let's consider that case. So what happens if A and B are both odd? Okay, then examine this equation first of all, and let's try to see what's wrong with it. Okay, then, oh, first of all, I guess, let me also just say, let me get to this in a second. I just want to say, well, C squared is even. Okay, which implies C is even. Let's just make that point. I mean, that's also coming from this equation, but let's take it. All right, so if this is odd, that one's odd. This is an odd plus an odd, and you would get an even. So in this scenario, we don't yet have a contradiction, but A, B are odd, C is even. And so now is where this lemma becomes useful. Because what the lemma says is that, according to the lemma, this is 1 more than a multiple of 8, and this one is 1 more than a multiple of 8. So if you add those together, you get, in fact, something that's 2 more than a multiple of 8. And so the lemma says this is something like 8k plus 2. Right? It's 2 more than a multiple of 8. Okay? Whereas the lemma also says this right-hand side is a multiple of 4. Right, because C was even, so C squared is a multiple of 4. And so the thing is that this left-hand side is not divisible by 4, right? That's the thing. So something that's 2 more than a multiple of 8 is in fact also 2 more than a multiple of 4. So it's not a multiple of 4. Okay, so this is a contradiction. These two facts, these are contradictory facts. Okay, so it cannot be that A and B are both odd, because that makes you run into this contradiction. So anyway, so now we're at the point where they have to be opposite parity. Like one is even, one is odd. Okay, so we know that. Okay, so one of AB is even, the other is odd. Okay, now they're kind of symmetric in this discussion, so we can relabel them if we need. So So it's kind of natural to just say, let's say without loss of generality, let's say B is even and A is odd. So B is going to be the even one, A is going to be the odd one. And anyway, the extra thing that follows, by the way, immediately is something we asserted here. Okay, so if we know one is even, one's odd, then it's going to follow as we've already made similar arguments. The right-hand side is going to be odd now, which is going to imply that C is odd. Okay, so we took care of this sentence right here. Okay. So now we have to explain where do these M and N's come from. So let's try to figure this out. Okay, so we're going to use the fact that B is even. So we can write B is 2 times something else. So we'll just call that thing B1. So sorry, B is twice B1. And then what we have is this. So I want to consider B squared, which is 4B1 squared. Okay, and then the point of that is this is, first of all, our main equation tells us B squared is C squared minus A squared. Okay, that's the difference of 2 squares. And difference of 2 squares, you could factor as C minus A times C plus A. Okay, now what we can do with this is a useful observation. So we could take this equation and divide out by this 4. Okay, so I'm going to write the following thing. So that follows from this equation, but anytime you're dividing stuff in number theory, you may want to figure out if you actually have integers around. And so here we know enough to actually to know that these are integers. Each of these fractions is an integer. So what we're in the scenario where A is odd, C is odd. Okay, A is odd, C is odd. If you subtract 2 odd numbers, you get an even number, and so it's divisible by 2. So this fraction is in fact an integer. Okay. And for the same reasons, C plus A is going to be an even integer, so it is divisible by 2, and that's also an integer. So just a very important remark here is that since A and C are both odd, both of these things, C minus A over 2 and C plus A over 2 are integers. So if you peek back at our formulas over here, you're about to see where M and N come from. Because if you believe these things are supposed to be true, which we do because we're going to prove it, but like we know they're supposed to be true. Like what is C minus A over 2 according to these formulas? Like if you take C and you subtract A, the n's cancel and you get twice m squared. So actually C minus A over 2 is m squared. And if you look at what's A plus C over 2 is, it's actually n squared. So they're going to come from this, but what's interesting over here is we have a product of 2 integers that gives us a square, and we're kind of saying that individually they should both be squares. And this is where our lemma is going to swoop in a little bit to help us out. So we're going to use one of our other lemmas in a moment, but what we actually need to know is that these are 2 relatively prime things. Okay, so we're going to establish this. We have to prove it. So here's the next claim. So we claim that the GCD of M and N is, no, sorry, not M and N, those 2 things. So C minus A over 2 and c plus a over 2. We claim that this is 1. Okay, so we want to establish this. And so we're going to make a similar kind of argument to the style we made before. Was to show this, we'll assume they have a prime divisor in common. So suppose P is a prime that divides both. So c minus a over 2 and c plus a over 2. Okay, we just have to see what's wrong with that picture. And we're going to make same kind of arguments where, like, once you know it divides both these, it divides all their linear combinations, and there's some interesting ones you can form. Okay, so then what happens is P will divide the sum. Okay, that's one interesting linear combination. But the sum of these two things is C. Right? So P would also divide C. And P also divides their difference, which we'll take in this order. This one minus that one. Okay, because that one's cooked up to give you A. Okay, what we want to do is somehow contradict the fact that the thing's primitive. But to get a contradiction, you have to know it divides B too. So that's going to follow as well, but we have to just say it. Okay, so further. P is going to divide the difference of their squares. So c squared minus a squared, which is b squared. Okay, if we know P divides a and c, then it does divide this thing, and that's b squared. But once you know that, if P divides b squared, this implies it has to divide b, again, because it's a prime. Right, so that's using fundamental property of primes. And so now you have a contradiction. Okay, so this all contradicts. That the GCD of ABC is supposed to be 1, and then somehow we're in a scenario where P divides all 3. Right, so that cannot be. So there cannot be a prime that divides these two things. Okay, and so where we're at then is right here. So we have b1 squared, that equation from over there. I'm going to write it down. We have this integer square is this product of two things, and these two things are relatively prime. Okay, so now we're actually, close one. Now we're in a position to use the other lemma today about perfect k powers. So by this lemma, whatever it's called, sorry, I just forget, 5.6 or something. Yeah, by lemma 5.6. What's true is that each of the two factors is a perfect square. And so each factor is a perfect square. Okay, and this is going to explain where the m and the n come from. So the first one is a perfect square. It's a square of some integer. Let's call that integer m. And the other one is the square of a different integer. Let's call that n. So this is true for some integers m and n. Okay, and then what remains to be done is to verify these three formulas. Okay, and also verify some of these extra things about m and n. So m and n is one's even, one's odd, and they're relatively prime. So let's see how much we can get done. But this is like where we conjure up the m and the n in this existence proof, where we have to like say why the m and the n exist. This is where they came from. And okay, so So anyway, if you look at, let's say, n squared plus m squared, this is c plus a over 2 plus c minus a over 2, which is c. Okay, that's one of our formulas we wanted to establish. Check that one off. And n squared minus m squared is c plus a over 2 minus c minus a over 2. Okay, that works out to be a. Okay, and furthermore, okay, what happens is b squared we know is 4b1 squared. Let's write this out. So b squared was 4b1 squared, and b1 squared was this. Right, which we just said this is 4 m squared n squared. Okay, so b squared is 4m squared n squared, so this implies if you take a square root, then we get our formula for b. So we got our 3 formulas for a, b, and c. Just checked off. We verified all of these are true. Why are they relatively prime? Why is one even, one odd is like the last things to clean up. Okay, and so at least for the relatively prime part, we know that if you look at this, consider the GCD of these two things. Well, these are those two things. So this is where we already put in some work. This is the GCD of c minus a over 2, c plus a over 2. We actually know that GCD is 1. And so what we know about m and n is that if you squared them both and compared them to each other, they're relatively prime. And that's enough to imply m and n themselves are relatively prime. Okay, and so anyway, what's the last bit is why is one even, one odd? I guess that follows from these formulas above, right? So since c is odd, let's just say this to close it out. Since c is odd, and we know that c is the sum of n squared plus m squared, right? It cannot be that n and m are both odd or both even, because the right-hand side would come out to be even. Okay, so it's going to follow that n and m cannot have the same parity. Okay, so n and this is exactly